Okay, thank you everyone. Good morning, and I'm Bruno Schmidt. I'm here to present today the EPFL logic synthesis libraries, which is the result of the combined work of many people in our LSI research group at the EPFL. So we have this collection of libraries for open source infrastructure to do logic synthesis. We have state-of-the-art algorithms. We target both conventional logic synthesis, classical logic synthesis, and also quantum compilation more recently. And our libraries, they have MIT license as far as I remember. So a brief of the outline of this talk. I will talk a little bit about logic synthesis. I'm sorry about that. Okay, this is
It's okay. Yeah.
okay. Yeah, hopefully the others, it was fine before. Well, let's try to go like that. So I'll talk a little bit about logic synthesis, then the motivations and goals of the libraries, then a bit about their implementation, and then give an example of how to use them to do something interesting. So logic synthesis, the process by which we take some abstract specification of a circuit behavior, and then we map to some technology-dependent logic primitives. So we have a specification, for example, in RTL, Verilog, VHDL, and then we want to map it into a FPGA. And we know that at some point we need to map it to some LUT network, there's LUT lookup table networks that lies inside the FPGAs. To do so, we use a bunch of different ways of representing logic. So basically we take our specification, we will use one of these ways of representing. You have products of sums, sum of products, logic networks, decision diagrams, and truth tables. And basically in logic synthesis, what you do is start with one representation, we do some optimization, we go to another representation, do some more optimization, and we keep transforming until we are happy, and we do some technology mapping. So what is the motivation and goals of these libraries? So we're doing research in logic synthesis, and we're a bunch of different researchers. We all did specific things. And what happened a lot is that we are all reinventing the wheel every time we wanted something. So basically, to reuse common functionality amongst us and amongst the community, that's what we are hoping for. So we really wanted these libraries to be easy to integrate, easy to adapt for our needs, and easy to contribute. They are quite modular, so each library will target one specific task in logic synthesis. And then we can compose them to create bigger frameworks. For example, Circuit, if you guys know about this, it is today just the composition of all these libraries to do logic synthesis. We are also motivated by some lessons learned from the development from Berkeley's ABC. Alan Michenko, its creator and maintainer, had given us a talk, and then where he shared with us all his experience and things that he would have done different if you were to implement ABC now. So we try to keep that in mind as well. So these are basically the 9 libraries that you have these days. And as I told you, each one will you target a specific thing on when doing logic synthesis. A bit about the implementation before we go on into the example. So they are modern implementations. They use C++14 or 17. They are header only. They have almost no dependency. And when they have some dependency, it's usually header only and shipped together with the library. So it's just like plug the folder and start playing with it. They are well documented and well tested. To some extent, we're still working on tests. It's a hard thing. So for this presentation, because of the time limit, I will only focus on these 4 libraries and show you how you can compose these 4 libraries to go from a specification to LUT mapping that can then be given to a placing route and then put on our FPGA. So let's move on into the example. We start with the specification, and then we wanted to end in this LUT network. And for the sake of making this presentation interesting, the LUTs will have a limit size of 3. Otherwise, it would be like too easy. We'll just use one LUT. So what is the function or the circuit that I want to implement is a combination of circuit. I'll call it prime 4, which basically take as input a 4-bit number, and will output 1 in the case if this bit is prime, 0 otherwise. It's quite easy example. Here I have some description of Verilog of this behavior, and then you might be looking at it and say like, okay, this guy has no idea how to do Verilog description, and there is a real good reason for that, but it's also true. I'm more of a VHDL guy. So this is the bird's eye view of what I want to show to you. We'll do it in 3 steps. We'll first take the description and then extract the logic out of it, a logic representation out of it, and then last we'll do the technology mapping. Hopefully if we have time, I will show how to do some optimization in between those 2 steps. So how do you do the parsing? For parsing, we will use the Lorena library, which has a collection of parsers for various file formats using logic synthesis. We have Eiger, Bench, Bliss, PLA, Verilog, but very simple gate-based Verilog, and that's the reason why the Verilog looked so weird in the previous slide. We also have some able to parse Liberty files. That's still a work in progress. And the library itself, it is lightweight and quite customizable. Basically, the parsers, they will read the input and invoke callbacks whenever a parsing primitive is completed. So you need something to interface with this library, and what we use and what we will use in this presentation is our logic network library, MockTurtle, that provide various logic network representations and implement several reader callbacks for Eiger, Bench, PLA, and Verilog. So now we will use the Verilog parser, and by parsing the input, we can get this network representations, which basically on your left, you have this an inverter graph. So you have the inputs on the bottom as the triangles. You have one output at the top, and a bunch of nodes in between in there that are 2 input AND gates and edges that connect those gates. And then when you have a dashed egg, it means there is an inverter. You also can use majority inverter graph representation that you have on the right, which the main difference lies on the fact that the nodes are 3 input majority gates. It also has this constant 0 node right there that is also present on the IIG, but as I didn't need to use it here, I omit it, and I will be omitting it for the rest of the presentation. But these are logic networks after optimization. Actually, when we read them directly, they look much messier, and then they would not fit in this slide. The IIG actually does. So basically, when we first read the IIG, when we first read the Verilog, this is the AND inverter graph that represents the logic of the prime 4 input. So that we talk about a little bit about the MockTurtle library, and it is based on this philosophy of 4 layers. You have a network interface API that basically define some naming conventions and methods for classes that implement the network structures, and with that allows us to implement the algorithms in a more generic way. This will be understood in a few slides. We have the algorithms themselves that use the API, and then we have algorithms for logic synthesis, optimization, and technology mapping, and then we have a bunch of network implementation. So you might want to represent your logic as an inverter graph, a majority inverter graph, maybe XOR majority graphs, XOR AND graphs, KLT networks, or whatever kind of network implementation you want to implement yourself. And as long as you keep to our naming conventions, all the algorithms that we have implemented there to do optimization and mapping should work. Lastly, we have this layer for performance tweaks, where you can specialize some algorithms to work better in some networks, and I will not go into details of this, and I'm not even sure if we are using this right now. So, okay, we have our inverter graph, and now what we want to do is map it. So we have a bunch of algorithms. We have cut enumeration, LNT mapping, node resynthesis, cut rewriting, refactoring, a bunch of different algorithms. And if you have no idea what this is, it is not such a problem because we are well documented. So basically you can go to the web page in our documentation, and then it will explain what the algorithm does, how it does it, in really details, and then sometimes too many details, quite verbose, but then you can understand and learn what's going on right there. So let's begin with the LUT mapping, and then basically our goal is to cut our Boolean network in a way that the different pieces can fit into our LUT3 primitive. And we call these pieces cuts, so we cut it into cuts. And there are many different ways to do that. So basically we could do it like this, and you see that our resulting LUT network would use seven LUTs. But of course, there are many ways of actually cutting a network. So what we do first is like we do cut the numeration, and we do it bounding some parameters. We bound the size of the LUT because we only are interested in LUTs with cuts with maximum of 3 inputs, and then we also give a maximum number of cuts because we don't want to keep enumerating different cuts forever. So we take this representation, and then we can enumerate a little bit more cuts, and then when you're happy about the number of cuts that we have, what we do is we select a set of cuts that will map the whole logic network. And our aim here, it is to find a good mapping with respect to some cost function that you can define. Maybe you're interested in have shorter critical path delay, or maybe you're interested in using a smart number of LUTs. So by selecting different cuts, instead of having this mapping, we could do it slightly better, or we can do it even better, and not only minimizing the number of LUTs, but the number of logic levels in this network. So by now, I could have, okay, I'm done, but there will be no fun, so let's look at how to do a bit of optimization using Mock Turtle. So for optimization, you do cut rewriting, and then basically, because we already presented how to cut the network, so what this does, this algorithm will try to rewrite cuts in terms of another set of nodes. So we'll take one cut, the cut is the subnetwork itself, so we'll try to minimize the number of nodes inside that cut. And for example, let's take, for example, this cut. We want to compute a replacement for it, so we want a function that implements the same functionality that it is being realized by this set of nodes. And the first thing we do is actually we want to represent more explicitly what the function that this cut is implementing it is actually doing. And for that, we use a truth table. So, and when dealing with truth table, Kitty library comes quite handy. It provides 2 data structures to manipulate truth tables. We have static truth tables, dynamic truth tables, and the main difference is that you know the number of variables at compile time or at runtime, and then some of its algorithms will be faster if you know at compile time what is the number of variables. It also provides you several algorithms to do some operations between truth tables, finding implicants, canonization, NPN, spectral. If you have no idea what that is, you can again look at the documentation. It is there, it explained. So we take the cut and we generate a truth table for it. And then we can generate the truth table by basically just inputting all possible input combinations and then see what happens in R, and then we get our truth table. And now we want to synthesize a new network for this that will implement the same function. And to do so, we use exact synthesis, which, given a specification, in this case the truth table, it will find an optimum Boolean network where the optimability is defined with respect to some cost function. So for that, we use Percy, exact synthesis library. It offers a collection of different SAT-solver exact synthesis methods for circuit resynthesis, design exploration, or function classification. It is easy to prototype and experiment with topology-based synthesis, different encodings, different SAT-solvers, backends, and parallel synthesis. So when we put this through Percy, it gives us a slightly better network, for this cut that uses, instead of 5, 4 nodes. So the algorithm of cutting rewriting will basically compute potential replacements like this for all cuts, and then heuristically select a maximum set of cuts that are non-conflicting between them, and maximize some of the overall gain that we're trying to get. So basically, in this example, what I'm trying to do it is minimize the number of LUTs that I will be using. So by applying the algorithm to the different cuts, we can actually get this network that can be cut and use only 3 LUTs in the end. So we were able to squeeze out one more LUT from our previous selection by using this optimization. So this is basically a simple summary of what we see. So you start from a Verilog, you extract the logic representation of it, in this case the AAG. You optimize your circuit using cut rewriting or some of the other techniques that we provide, and then you map it to a LUT network. So far, everything is quite easy, and then I have make it easy and mask some of the details of the implementation, but talking is easy. How is the code look like to do all these steps that I just told you? And it is basically this code. So here we first load the network, and we parse the input and create the network. Then we do the cut rewriting, and when you do cut rewriting, you end up with some dangling nodes in a network, so you need to clean it up afterwards. And then you map it to your to LUT. It is as simple as that, and then afterwards you can write in one of the formats that can then be the input for some placing routing tool that comes afterwards. So here we have some other example that also use Alice, and most of showcase and examples you can look at the GitHub repository. So basically, this example provides a simple shell interface using the Alice library. It loads some truth tables, and then do some load truth tables from binary and XML decimal strings, load from bench, do some NPN canonization, and then you can play around. And then to have something like this, it would be more kind of a tool. It only takes the 268 lines of code from the user's point of view, for the people who are actually composing the libraries and doing their thing. So with that, I came to the end of my presentation. I might use this. I do have some other slides on the other, a bit on the other libraries, but as the slides are not so nice with this, so I think we can end it here and then go for the questions. So does the tool handle multiple output? Yes, it does. It does handle multiple outputs. It is just that for these slides, for the sake of simplicity, we're just using one output, but it can handle multiple outputs.
How do you weave the modules? Are they connected directly? Can I only connect this module to that module, or is there a more general way of connecting them? Is it through global variables? Because the example was not very clear of the code.
So, yes. So how the modules connect to each other, is that what you're asking? So basically, for example, Mock Turtle already has embedded in it some of the other libraries. So Mock Turtle already has the Lorena library inside it, and KD and Percy. You see that Mock Turtle, because of what it does, has most of the other modules already in it. So basically, they have their own namespace there, but they already come with the code itself. I don't know.
They are pre-baked.
Yeah. So exactly. So when you get mock turtle, you get almost everything, if not everything. But maybe you don't want to do with logic networks at all. You want just truth tables. So you can only you don't need all the rest. So you can only take Kitty. Mock turtle will be the one that has everything kind of. It is when everything comes together. But Alice. Then when you have Alice, then you have the shell interface, and then all this. It does logging. You can create commands and stuff like that. Also with Alice, you can interface the code with Python. So you have Python bindings as well. So you have some flows that use Python, and then you can easily script and hack some of these optimizations and how together.
Can you override the cost functions, for example, specifically for an FPGA where you want the cost optimized?
Yeah. So the question is if we can override cost functions. Yes, you can pass cost functions as parameters. And then that's basically what we do in some of these algorithms are also using in this quantum compilation flow. And then in quantum, we do use different cost functions. So they are configurable. As long as there's an object that can be called as a function, you can pass it as a...
More questions?
Any more questions?
Okay. Yeah.
Oh.
What, how does this fit into the broader system? Has there been an attempt on Yosys integration? How does it interact with the rework that's been done over the past couple weeks on building a new synthesis engine for Yosys?
So how does this fit in a broader system? That's the question. So basically, whenever you use something like ABC, you could more or less replace it. If it is in the logic synthesis, you could more or less replace it with the libraries that we have here. ABC has more things in form of verification as well. But for example, in this last semester, we gave there was a lecture in ADA in EPFL where the students were asked to use those libraries with Yosys. And we definitely want to do more integration with Yosys. We just do not know how to use the Verilog parser in Yosys to harness and get all the different combinational parts. And then we could do optimization there. But the goal here is just like to expose ourselves and then try to put ourselves in this other flows. And then we're quite open, and we have been talking to other groups that are willing to use those libraries in their whole flows.
I guess the lookup three tables were just an example, and it's
Yeah,
mapped to different.
exactly. So basically, actually, if I wanted to do this example, I would still need to tweak a little bit because the default is lookup table of 4. Oh, okay, sorry. I need to repeat the question. So the question is if I can change for different sizes of lookup tables. And yes, you can. You can configure yourself what the size of the lookup table will be.
Have you considered using an intermediate representation as an input and output so that you can plug in multiple workflows like here RTL?
So not really, basically. So have we considered to use some kind of intermediate representation to plug in other flows? And so we already support many of the intermediate representations in logic synthesis. Basically, some of those flows can output a BLIF file, for example, and then we can read it. You can parse it BLIF, and then we can output BLIF. So that will be more or less this intermediate representation you're talking about. All the other RTL languages, more in between, I don't know. The problem with RTL languages is the parsers are quite complex and requires a lot of work to put in there, and then we don't do it currently.
So I think also the optimal mapping should, is correlated with the timing. Is there some timing?
So the optimal, the question is says that the optimal mapping should be correlated with timing. So we use some sort of abstraction of it, basically the number of logic levels in your network, right? That more and less will tell you about delay. We do not know exactly what it is because to do the exactly timing, we need to do the placing route. So actually this is the reason why we are doing this Liberty file parsing, where you can get this information back and then try to do, and then you can loop around and then use timing information, more precise timing information to guide your logic synthesis and optimization algorithms. We are working on that.
Any other questions? No? Okay, let's thank Bruno again.
Thank you.